So if I go for the command, I go to analyze. So you can follow the handout. And then I go to regression and multinomial logistic. See that? Okay. Our dependent variable is me. Always me. Mammography experience. Okay. And what is the reference group? We have to define the reference category. It's a neighbor, right? Neighbor, I coding neighbor. What is a neighbor? Here, neighbor is 0. So it should be the first, not the last. Okay. So I change this to be first. So the reference group for dependent variable, the program allow you, but for independent, they don't allow you. Okay. This is just for dependent variable. And then, but this one is good that we can custom any group, any code. Okay. And then I continue. Okay. Then, the statistic, I think we can do the goodness of fit for the statistic. If we click on classify goodness of fit, okay, to check whether that our goodness of fit is that okay. And then we continue. Criteria, nothing, huh? Don't have to do anything. Option. No option. Save. We don't want to save the line. This one we can save the predicted, the probability. But let me go to the main, the result first. Bootstrap, nothing. And factor, what is a factor? Factor is for categorical variable. So we choose which one? Has to be a family history because it's a factor, it's a categorical variable. His one, nah? Pick his one. His one, the last one. And the covariate is perceived. Okay, and then we click OK. Okay, look at this is just descriptive. Okay, and how many our data? 412. Now 412 cases. This is a minus. This is a minus to log likelihood. You see we have a now model, intercept model. Goodness of it is right here. It's okay because our p-value is 0.968, so it's not significant, right? So this means our model fit well. This is the R square. And this is a likelihood ratio test. This is like the improvement test. We have the intercept. This is a minus to log likelihood of null model is 93 point something. But for the PB, this is the minus to log likelihood for the model with the perceived benefit only. And the last one, 104 here, this is a minus to log likelihood of the model of history of family only. And the chi-square here is for the improvement test when each model compared to the null model. So the chi-square here, the 33.327 is the improvement test of the model with perceived benefit compared to the null model. For the chi-square 10.931, this is the improvement test between two models, the model with history and null model. And there are the significance. So this means that these two variables should be significant. But anyway, when we look at our final model here, so you will see this is the result of the model. Let me go to the, okay, we already did that. Here. The classification I will talk later. This table. Now you can see for two blocks, right? In the table of the parameter estimates. This is the within 1 year. This is for over 1 year ago. So what does mean? This means the logic model for within 1 year and never. The second part is over 1 year ago compared to never. Because our reference group is never, right? So now we have two logic models. So when we write a model, we just write a model separately for each part. Okay, so the first logic model is this part, the first part. This is the second part. Okay, so can you look at the PB? Is significant? Yes. And what about the history? Also significant. And what about over 1 year ago? Also significant. But we will get the different beta 0, beta 1, right? For each one. Okay, so this is the model. Can we write a model for these two logic models? Yes, we can, right? Okay. I'll let you write it down. So you can write down the model now for each logic model, okay? And the never is the reference group. This one we just read the output the same as binary logistic regression. Odd ratio equal to exponential of beta. No minus beta, because this one is straightforward. For each part is set of logic model. Okay. And for the classification table, I think in our output we don't have that, right? No, okay, we go to the command again. We can, in the command under statistics, we click on the classification table, we will see that. This is the same as the classification in logistic regression, but just more groups. And then we click the continue. If I run again, you will see the classification table in the last part. Okay, can you get that? How can we interpret this classification table?
Analyze.
226, so what does it mean? 226, the observe or the data tell us that we have 226 subjects never go to have the mammogram. But the model also predict that they don't have that they never go to have mammogram, right? So, and what about this one? 8. Can we interpret it? 8. Observe said that never, but the predict said within 1 year, right? So this is the correct prediction or wrong prediction?
Wrong prediction.
It's a wrong prediction, right? So these are wrong. And what about 86? Right or wrong?
Right.
Also wrong, because observe said within 1 year, but predict said never. So this is wrong. So the diagonal line is the right one, the right prediction. Now we have 3 groups. If your model is good, you should get a big number at the diagonal line here. That means you observe and your prediction same category of your outcome. Okay? And the number, so this is the overall percentage. Overall the percentage, this is the percentage that the model predict correctly. Yeah. How many of the neighbor? This one, 92%. How come? The model predict that never have the mammogram. How many? 226. And what is the total number of the neighbor? We look at here. This is the actual data, right? The observed is 2, 3, 4. In your data, you have 2, 3 number of subjects that never have the mammography here from your output. And how many from the prediction? 226. So 226 over 234 equal to 92%. Here. This is the overall percentage. Okay? 92 here is come from 226 over 234. Is come from the right prediction based on your model compared to the observed data. So now you can calculate here. So this is 8, right? 8% come from 8 over within 1 year, right? How many within 1 year? 104. So it had to be 8 over 104. This is the observed. This is the information from the observed. But in this table, that this is the prediction and the observed, we cost together, do the cost tabulation. Okay, and then we don't have over 1 year ago that the model not predict this category at all. But how many we have in our observed? Over 1 year we have 74. But our model never predict because 0, 0, and 0. So we get 0%. Okay. So if your model is good, you should get a big number of the overall percentage. This means that your model predict very well only for the category never, but not good for the category over 1 year ago. You misclassify your model. Okay. Now after we got our model here, how can we interpret? We just interpret straightforward of the odd ratio here. Okay, so please based on slide number 30, 39, and 40. Look at each part. So when we interpret, we will interpret each part. Now I will look at the first part. Within 1 year, we look at the effect of the family history and perceived benefit. Okay, at the first part, that we compare within 1 year and never. This is the first part of the output. Okay, within 1 year and never, we have two variables. The first one is the family history. We got the odd ratio. What is the odd ratio? 3.3, right? Here, 3.3. So the odds among women with a family history of breast cancer having a mammogram within the last year is 3.3 times greater than the odds among women without family history. Okay. Or women with a family history of breast cancer are 3.3 times more likely to be frequent user of mammography screening than women without family history. Okay. This is for the family history. If we compare within 1 year and never, we got odd ratio 3.3. Okay. And what about over 1 year and never? Okay, now I will look at this part for the PBO, for the family history, 3.3. And then I will compare over 1 year ago and never. The family history is 2.6. You see, 2.6. I'll round it up to 2.7. Okay. So the odd among women with a family history of breast cancer having a mammogram over 1 year ago is 2.7 times greater than the odd among women without a family history. Okay. So the odd ratio is different when we compare the different groups. Okay. And if you compare PB, perceive the benefit. Okay. What is the odd ratio for within 1 year and never? We got odd ratio 0.71. Again, 0.71. Because it's less than 1, I will do in percent again. Okay. This means that, okay, here, this is because perceived benefits, lower score is better, right? Because we got the odd ratio less than 1. So this means a 1 score increase in perceived benefit of women, 1 score increase is associated with a 0.71 decrease because this is the odd ratio less than 1 in the odd ratio of having a mammogram with the last year. Or if we make it more understandable that the odd ratio for perceived benefit of women estimate a 30% reduction in chance of having a mammogram with the last year, because this is within 1 year, per 1 score increase of perceived benefit. Okay, so we just interpret in the same pattern that we did before. This is because our odd ratio less than 1. This is for the 1 year, within 1 year compared to never. We got the odd ratio 0.71. And what about over 1 year and never? We got the odd ratio 0.82, different number. Okay, so we interpret in the same pattern. Okay. So this is just example. Nah? You can write in another way, anyway, that to make the same meaning. Okay. So the odd ratio for perceived benefit of women estimate 18%. 18% is 1 minus 0.82 times 100. Reduction in chance of having a mammogram over 1 year ago per 1 score increase of perceived benefit. So this means that the score of the increased score of the perceived benefit, it will reduce the chance of having mammogram within 1 year and over 1 year. Okay, so I think this is all, and you can practice for other variable